Three, two, one. Okay. All right, here we go. Now, we've talked about the cells that make up the brain and the nervous system. That was chapter 12, I think. And then we studied the spinal cord, which is really the lowest part of the brain. And then we just kind of finished studying the brain itself, okay? And we have two more things to learn about. One is, well, how do all of these pathways hook up and what routes do they take and how do they work? And then the last chapter, which we'll do next class period, I hope, if we can get completely through this one, this period, is called the autonomic nervous system. And I've talked to you about the autonomic nervous system before. It's the rest and digest versus the fight or flight. And it's the reason that the autonomic nervous system is so important is because it's the one that most all of our drugs work on. All of the drugs that we use in medicine that have anything to do with the brain, sleep or Parkinson's or anything really, Alzheimer's, they all work through the autonomic nervous system. So we'll talk about that later. This is my daughter. I had lunch with her the other day. Monday. I think I've told you many times, she's a CPA down in Portland, so I go down there and have lunch with her once in a while, and we catch up. She's getting married this summer.
Congrats.
We're excited. Okay. So let's talk about the input and output to the brain. That's what we're going to talk about here. And let's start with talking about the two major divisions of information coming in. There's the afferent division, which is all the information that's approaching the brain, A for approaching, coming in. And then there's the efferent division, which is all the information that's flowing out. Okay? So, to learn about the afferent division, I think we're going to do this first, and it deals with the receptors. What are the really little tiny receptors in your fingers that sense things like pressure and temperature and so forth? And then the neurons, those sensory neurons that carry that information up to your brain. And then what are the pathways? How does that actually go through the brain, up through the spinal cord, up to the brain to get to the cerebrum where you recognize it? Efferent system comes from the brain also, goes down through nuclei. Remember, nuclei are just collections of
Cell bodies.
They're collections of gray matter within the brain. Motor tracts are bunches of axons that are carrying information down to the muscles. And then finally the motor neurons that are making the muscles contract. You remember those muscle groups? Remember A, B, and C, and one would rest, so the next one. Back in the muscle chapter, we'll talk a little bit back. We'll go back to that a little bit. So let's talk about the sensory receptors. The sensory receptors are pretty specific cells, pretty specific receptors that pick up the environment for us. Usually what happens is if a receptor, say we're talking about a thermoreceptor and it's a temperature receptor, and it notices that it's pretty hot here, well, that thermoreceptor will pick up that information and it will cause a axon to fire off. It'll send an action potential. It'll go all the way up here to the spinal cord. It'll go to the, where does it go?
Thalamus?
No. No. Where's the cell body for that sensory nerve probably going to be found? Dorsal root ganglion, that's right. And it's going to go on into the spinal cord and go up eventually to the thalamus and then eventually to the cerebrum if it comes to our level of consciousness. So that's kind of what we're talking about here. Somatic nervous system, this is just is going to be the next part. SNS, the somatic nervous system, is basically the motor control of the muscles that we can control, the skeletal muscles. All right. As far as senses, we have basically 6 of them. Temperature, pain, touch, pressure, vibration, proprioception. I'm probably not going to ask you to list those, but you will need to know a little something about each of the receptors that picks those up. We also, the reception, here's two words you need to understand. One is called sensation, and that means that the things are sending information up to the brain. But then there's another term called perception. Perception means the ones that you actually are aware of in your cerebral level. So you can get lots of sensations coming into you, and you're all getting zillions of perceptions right now, sensations, but you're probably not getting all that many perceptions right now. Those are the ones that are actually making it to your brain. And for those of you that are asleep, you're probably not getting any. We also have some special senses, and in addition to those general senses we just talked about. I don't think anybody's asleep in here. I was just kidding. Olfaction is smell, vision is sight, gustation is taste, equilibrium is balance, and hearing is hearing. Those are the special senses. We will cover all of those in the next chapter. It'll be covered on the next test. Okay? We have an entire chapter called Special Senses. Imagine that. Okay, so each one of these receptors that lives out in the periphery of our skin, for example, it has what's called a receptive field. Now, what does that mean? Well, a receptive field is the area that is monitored by a single receptor cell. The larger the receptive field, the more difficult it is to localize stimulus. Now, what does that malarkey mean? Yeah.
The bigger the receptive area, the harder it is to pinpoint the exact location. So if I touch your back in one spot, you have a lot of reception in your back, and larger areas versus your lips have a very narrow receptive area.
That's pretty well said, actually. Let's look at this picture right here. Here is receptive field number 1, and this is receptive field number 2. If you touch the skin anywhere in that blue area, it's going to send a signal up this axon right here and up to your brain. Your brain will not know whether it came from here, or whether it came from here, or whether it came from up there. It'll just know that it came from somewhere in that receptive field. And this is a pretty big one, right? In certain areas of our body, however, these receptive fields are very, very small. And one of the things that we do in medicine, it takes a really complicated piece of equipment here, and it's called a paperclip. And I'm going to test you here, okay? Now I want you to close your eyes and look over that way. And here's what I want you to tell me. I want you to tell me whether I touched you with one thing or with two things. Okay? So you just say one or two. Okay?
1. 2. 1.
Okay. Now, I was touching her with two, but she was interpreting it as only one up here on her arm. Whereas down here, she got every one of them right. And the reason is because the receptive fields down here on your hand are much smaller than they are on your upper arm, and it certainly would be on her back. In fact, on your back, oftentimes you can touch people with things that far apart, and they still think you're only touching them at one spot. That's because their receptive fields are that big. And if both ends of the thing are touching within the same receptive field, they're going to only feel one. So it's kind of a way to measure how sensitive people are. It's also commonly used in diabetic testing, because diabetics tend to have damage to their nerves going down to their feet. So when you go in as a diabetic, you'll probably get some kind of a sensation test, whether it's with this or whether it's a little tiny pin or something. How many do you feel, or do you feel it, do you not feel it, do you feel it, do you not feel it, Okay? That's where it comes from, receptive fields. Now, in all in honesty, the back, in your back, the receptive fields can be this big around. On your lips and on your fingertips, they're usually about 1/2 millimeter. I mean, they're really small. That's why we have such fine sensation with our fingertips and with our lips. Okay? Adaptation is this process that we've already talked about in this class, I know, in which your nervous system adapts very quickly to stimuli that are both painless and constant. And you've heard me talk about the fan in the projector and how, yeah, you can hear it if you listen for it, but I bet most of you weren't sitting here listening to it all the time because it's constant, it's not painful, it just kind of fades away because your brain gets used to it. And that's really what adaptation means. Yeah.
Can your brain become accepting of a dull pain after a while?
Yeah. I think that's why people have different pain tolerances, is that we can kind of accept dull pains. So basically, the stimulation that a receptor produces these action potentials, and if it's a thermoreceptor, it interprets temperature. If it's a chemoreceptor, it interprets chemicals. If it's a pain receptor, it interprets pain. It can only interpret the one thing that it's made to perceive. And then the route that it takes up to your brain tells your brain where it's coming from. Because your brain knows that that one particular axon that goes from this finger goes up here, goes through the dorsal root ganglion, goes through the thalamus, comes up through your brain. It knows exactly where it's coming from. Why? Because remember that baby thing I talked about one time? That's how we figure out where all this stuff is coming from, is we touch ourselves a bunch of times. A few 100,000 times. All right, so then your perception of it is the nature, depends on the path that it takes to get to you. Exteroreceptors are a group of receptors that provide information about the external environment. Those are the ones like the pain and temperature that I've been talking about. Proprioceptors, I've told you before, has to do with the position of your joints so that you know where your joints are. Interoreceptors are the ones that monitor your abdominal visceral organs. So if you get abdominal cramps, for example, that's picked up by interoreceptors. And just so you know, you don't have very many interoreceptors. You may think, oh my gosh, that was the worst pain I ever had, but the fact of the matter is you go months and months and years and never feel anything inside of you. Right? And because of that, I can't say exactly where my spleen is. The only way I know where my spleen is because I read about it in a book. And I saw a few, took out a few. You know, but the fact is, we don't know much about what's going on inside because it's not like we're not like that baby that can touch your spleen a bunch of times and figure out what the spleens feel like, right? Proprioceptors we've talked about. I think I've already said all of those things. Here's some more nociceptors or pain. So think of that word noci. Whenever you see that, think pain. Thermo, think temperature. Mechano, think physical distortion. In other words, you can feel whether the skin on the back of your elbow is stretched or not. That's a mechanical receptor. Chemoreceptors are chemical concentrations. Nociceptors, pain receptors. They're very common. They're very common in our skin. They're very common in our joint capsules. Has anybody ever dislocated a joint? Did it hurt?
Very much.
Very much, right? Because we have lots and lots of nociceptors in our joint capsules, in the periosteum of our bone. That's why a broken bone hurts so much, because whenever you break your bone, you've also torn the periosteum. Remember, that's the outside layer of the bone, and so forth. I'll just leave that at that. Thermoreceptors, these are usually just free nerve endings. These aren't very specialized receptor cells like most of the others. They're just free nerve endings. You'll see what I mean by that in a minute. And they're found in a bunch of different places. And you notice this seems weird, doesn't it? The hypothalamus is listed as a place where there's a lot of temperature receptors. but just remember that that's really where our body interprets our body temperature. By measuring the temperature of the blood in the hypothalamus, it says, hey, we're getting too hot or we're getting too cool. And if we're getting too hot, it's going to start shunting the blood in different directions. It's going to make us shiver. If we're too cold, it's going to make us sweat if we're too hot. But a lot of that happens right there in the hypothalamus. Okay. Here we go. Let's run through these 6 different types of tactile receptors. Free nerve endings are that you can feel touch and pressure with them. They're right up in the skin. They look like this, like these guys right here. Free nerve endings right over there. They're just little nerves that come up to an empty end. They don't have a fancy organ on the end of them, and so forth. The root hair plexus, we talked about that, by how sensitive our root hairs are. You feel a little bit of breeze. The reason you feel the breeze is because it's blowing your hairs around a little bit, and it takes very little distortion of your hair to signal that something's going on up there. So here's a root hair plexus right here, and it looks like that, and you notice that it's always within the base, the root of the hair. And so the sensation is down here, but if this hair even up here gets moved, it will sense that. Tactile discs are also called Merkel discs. You need to see these in lab. You'll see them on the microscope, and some of them are on the models. Merkel disc, a tactile disc, looks like this. And I would only say that once you see a Merkel disc, you'll never forget it. They're pretty obvious once you see it. Yes?
Are they like do something with Merkel cells? Aren't there Merkel cells in Michigan also?
Yes, there are.
So those are they the same thing, just Merkel cells?
Yeah, here you go. See, Merkel discs, tactile discs with Merkel cells in them. Then there's these tactile corpuscles called Meissner's corpuscles. They are fairly large structures. You can see they're most abundant in the eyelids, lips, fingertips, nipples, and external genitalia. And they look like tactile corpuscles. Is that these guys? Here's a tactile corpuscle right here. These are, once again, you see them right in the dermis, which means they're below the epidermis. Remember, this is the stratum germinativum, the lowest level of the skin right there. And these are the tactile corpuscles. Once again, once you've seen them, they look like this. They're always at the same place. They're always just below the dermis-epidermis line. Yes, ma'am?
So I thought Merkel cells were only found in hairless skin. Is that
In hairless skin?
like around your eyelids and like your fingertips and palms?
That's why most abundant eyelids, lips, and fingertips.
But can it be found where there is hair? It's not.
I don't know. That's a good question.
Okay.
Let's try to study that
Okay.
and tell everybody. So I'll know. Pacinian corpuscles, also called lamellated. These are really easy. Once you've seen one of those, you won't forget them either. These are very, they look like an onion skin, lots of layers to them. They are a little bit deeper in the skin, and they sense deep pressure. So deep pressure is picked up by the Pacinian corpuscles. Let me tell you one thing. This is a lab test question. The best place I've ever seen Pacinian corpuscles is in the pancreas. Now, pancreas is a digestive organ. We'll learn about it next chapter. But just remember that we've got some slides down there in the lab that are actually pancreas slides that also say Pacinian corpuscles, and you just ought to look at it because they're so beautiful and so big. Okay? Here's what a lamellated or Pacinian corpuscle looks like. You can see it here. It looks like a peeled onion, or with a single dendrite sticking out, and it's a thing that interprets pressure. When that onion is squeezed, it presses on the dendrite in the middle and sends off the message. Ruffini corpuscles are deep in this reticular dermis, the deep dermis, and they detect pressure as well, and they look like these guys right here. I'm not sure I've seen those in the microscope labs very well. Have you ever seen one of those down in the lab? I haven't either, so I probably wouldn't worry too much about these guys. Baroreceptors measure pressure. You will not see these in lab. These are usually found in the walls of a blood vessel, because that's where we detect blood pressure. It's from how much stretch is on the wall of a blood pressure vessel, a blood vessel, and they then send messages saying either the blood pressure is too high or the blood pressure is too low, and then your autonomic system can adjust to bring it back to normal. Proprioceptors, I know I have talked to you about several times. It tells you where your joints are. It's how you know how many fingers I'm holding up. I do know that I'm holding up 2 fingers back there, and that's because I know where my fingers are, and you do too. You know where your joints are. Several groups of proprioceptors here. Where are they found? Well, muscle spindles are these receptors that are within the muscle itself. So in other words, if I have my biceps here and my biceps is out there, I know that my biceps is kind of stretched because I have these muscle spindles. And then if I pull it up like this, I know that my biceps is more contracted because of my muscle spindles. Golgi tendon organs are down here in the end of the tendon, and they're also telling me whether my arm is bent or whether it's straight, depending on the amount of tension that's on it. And finally, there are lots of receptors in the joint itself. So within my elbow here, my elbow, those receptors are telling me, okay, my elbow is straight, okay, my elbow is bent. So that's the 3 ways that we know where we're at, if that makes sense, or at least where your joints are at. Chemoreceptors, I think that when we talk chemoreceptors, you should just know we're only talking about really 2 things. Mostly we're talking about pH and carbon dioxide and oxygen. I would tell you that by far and away the most important one of these is carbon dioxide. We know what our carbon dioxide is level all the time. And if it gets even a little bit low, we breathe less. If it gets a little bit high, we breathe a few extra breaths, it blows off the extra CO2, and our CO2 comes back to normal. We can control our CO2 level perfectly. We'll learn about this in depth when we get to the respiratory system in 233. But just know that really the only 3 things our body, the only 3 chemicals that our body can test for on an ongoing basis are the pH, in other words, how acid we are, carbon dioxide, in other words, are we ventilating enough, and oxygen. Obviously, oxygen is important, but if your CO2 level is normal, your oxygen level is going to be normal most of the time. Okay? Did I tell the story about Payne Stewart in here?
Mm-hmm.
Payne Stewart was this golfer. He won the U.S. Open, won a couple of PGAs, I think. He always wore knickers on the golf course. You may remember him from that. He's kind of a really nice guy. And he went to a golf tournament down in Florida with a couple of buddies, and they got in a private jet, and they were flying to the next golf tournament, which was somewhere up in Minnesota or Canada maybe even. And the Air Force got these calls that there was this plane flying out of control, and they hadn't been able to get any voice messages back from them, so they scrambled a jet up to fly alongside this private plane, which was on autopilot. It was just flying across America, and they looked inside, and everybody was asleep. The pilots, the co-pilot, and all the people in the plane. The plane had decompressed, and they didn't have enough oxygen to breathe. Now, their CO2 monitor they probably continued to ventilate enough, and that's the one you really notice, because they kept their CO2s normal, but there wasn't any oxygen in the air, because they were up at about 25,000, 30,000 feet, and there's just not enough oxygen up there. And they all died, and the Air Force guys just kept following them until the plane ran out of gas and it augered in. And so the point being that, yeah, we can detect things, but the one we usually detect is carbon dioxide, but that will not tell us whether or not there's enough oxygen in the air, which there wasn't in their case. Wow. Okay. Wouldn't it be nice if we just had monitors for all of this stuff that we could just kind of like controls on a dashboard and check? Well, we don't. We don't have any of that stuff. Let's talk about different first order, second order, and third order neurons. And what this really means, and what I want you to get from this, is the fact that most sensory pathways, in order to go from that finger out there that we burnt or got hot, that message is probably going to travel through 3 nerve cells to get to your brain. Okay? The first neuron is the sensory neuron, and it's going to have a cell body, and that cell body is going to be located in the dorsal root ganglion of the spinal cord. And remember, these are what are called bipolar neurons, right? And so if you look at them, they have a really long dendrite like this that comes from your arm. It comes up here. Here's the cell body in the dorsal root ganglion. And then it goes into the spinal cord, right? And it's sensory, so it goes in up here at the top. And it goes here, and it's going to synapse with another cell, the second order neuron here. And that neuron is going to probably cross over at some level, and then it's going to go up to the brain, and it's going to go up. Let's say it's going to go out here. Let's see, this is sensory, so it needs to be out in here somewhere. And it's going to turn and go up to the brain, and then when it gets to the thalamus, that nerve is going to synapse again, and then that third synapse is going to carry it up here to the cerebrum. Right? And then we'll know that our finger got hot. Okay? First order, second order, third order neurons for sensory. Okay? For motor, it's just going to be usually 2. We'll talk about that in a second. So if the sensation is going to reach our awareness, the second order neuron is going to synapse on a third order neuron in the thalamus and take it up to the cerebrum. Remember the basics. I was very specific when I teach spinal cord. I just want you to know a few things. I want you to know that this is the dorsal root ganglion, and is that sensory or motor?
Sensory.
Sensory. This is the ventral root. It's always motor. And if you take the spinal cord in total and just divide it right across the middle like that, right through the central canal, everything above that is sensory, and everything below that is motor, which means this is all sensory gray matter, and this is all motor gray matter. This is pretty much all sensory white matter, so it's all going up to the brain, right? Sensory. And this down here is mostly motor, and it's going down to the muscles. Okay? Yes?
You say the motor is, the neuron you say is unipolar. I mean bipolar, is it unipolar when it carries the sensory to the central nervous system? Or is it bipolar?
Bipolar. Isn't that what this said? It doesn't say. But yeah, the cell body is here, and it's got a long dendrite, and it's got a long axon. And I think these are called, aren't they called bipolar neurons?
They usually polar because the dorsal ganglion body stick out. If it's bipolar, I don't know, for the lab book.
Maybe I'm saying that wrong. Let's talk about that in lab. Let's make sure we got that straight. That's probably my fault. Let's talk about the homunculus for a minute. Homunculus is a wonderful word. I don't know why I like it. Homunculus.
Big brain.
Yeah, it's kind of a functional map of the brain. And we have a sensory homunculus and we have a motor homunculus, okay? Now, the reason that it's a very distorted looking person in this homunculus is because different areas of our body have different amounts of sensory input coming in from them. So if you look at this guy up here, this is the homunculus, this is the sensory homunculus, and this always breaks my heart that the genitalia are so small. Like, they seem like they should be bigger. But anyway, I mean, it seems like there's a fair amount of sensation coming from that. I'm just saying. And then you notice that the toes and the legs and the chest and the back and so forth are all relatively small in relation to how big they actually are, right? And then you come down your hand here, and your hand is getting a little bigger because our hands are pretty sensitive. We can feel pretty well with our hands. How do you feel? With my hands. And then your fingers are getting bigger yet. And then our face is bigger. We have lots of sensation on our face, right? And our jaw and our teeth. If you ever had a toothache, you know that that's pretty amazingly painful. And then our tongue. And our tongue is really amazingly sensitive. Because as we chew up stuff, think about it the next time you got a piece of steak in your mouth. Your tongue can feel the steak. It can feel for the tough areas that you haven't bit through yet. And your tongue can move that piece of meat around with such incredible talent so that the next time you chew, you know, you'll get every last little area in the meat that was tough until you've chewed them all. Then you'll push it back to the back of your mouth and swallow it. So the tongue is kind of the most, in many ways, it's kind of the last and one of the most sensitive thing. So going back to what we were just talking about with the sensory nerve coming in, here's your first order nerve coming in, dorsal root ganglion, turns inside, goes up. This one goes up to the nucleus, somewhere up in the lower brain, in the medulla oblongata here. And it synapses here with the second order neuron. It crosses over from left to right at this level, at the medullary level, and then it goes on up through the mesencephalon to the thalamus, okay? And it synapses here for the second time, entering into the third order neuron that carries the information all the way up to the cerebral cortex, okay? When you flip through your book, take a minute and look at these pictures. I think they're very helpful to help you understand this, how this works, and kind of ties in the different parts of the brain to some degree. So just take a minute to look through that. So what's the point of this homunculus? Why are different things different sizes? And if you thought about it ahead of time, would it have made sense to you that the face, lips, jaw, and index finger get the largest part of the sensory cortex? Yeah, it probably would. And that's why it works that way. Now, a couple more things about pain, because we're talking about sensation. Yes, I feel your pain, I know. Referred pain. Referred pain means that oftentimes we feel pain in one area, but it's not really coming from that area. It's coming from another area. It's referred to that area. The pain of appendicitis, your appendix lives down here in your right lower quadrant, but I believe in every case I never saw a patient who had the pain start there. The pain always starts kind of just diffusely in the center of the abdomen, and then as the appendix gets more and more sick and it starts irritating the peritoneum of the right lower quadrant where it really lives, then your brain kind of figures out, oh, well, that's really where the pain's coming from. So the pain finally goes, 8 or 10 hours later, it goes into the right lower quadrant, and then you can make the diagnosis pretty easily. So that's what, there's just, several examples of referred pain that are really common. You know that many times people who have a heart attack have pain that either comes down their arm, down their left arm, or it goes up into their jaw. In fact, in women, they're finding that the number one symptom of a heart attack in women is pain in the jaw. And that's why we misdiagnose heart disease in women a lot, is because a lot of folks don't know that, and they don't think, most of us don't even think heart attack in women, because it used to be a lot rarer in women than it was in men. But then you guys all started smoking as much as the men, and you caught up. Congratulations. Liver and gallbladder get referred either to the top of the shoulder. Why would it be referred to the top of the shoulder? It's because it irritates the diaphragm, and the diaphragm refers to the top of the shoulder. You guys ever had what's the thing you get when you're running? A stitch or a side ache? Yeah. And a lot of times it's in the top of your shoulder. That's because your diaphragm is overstretching and working too hard and not having enough oxygen, probably. But I can tell you, whenever I would interview people with gallstones, I would say, well, what was your pain like, ma'am? And she'd say, well, gosh, it starts in my tummy. It just feels so bad. I get nauseated. And then it just kind of goes. And if they do that, if they make that motion right there, that's what it is. It's their gallbladder. I never, ever saw that not be their gallbladder. And we'd order a gallbladder ultrasound to verify they had gallstones, and we'd operate on them and take them out. But pain radiating through to your back from the gallbladder is really common. Men will oftentimes come in with pain in their testicles that is a kidney stone. It's caused by a blockage of their ureters. The ureters have the same innervation as the testicles. And women sometimes get it too. Women, it'll radiate into their labia majora down there. And it's the same, for the same reason, it's referred pain. Yeah?
How come when a guy gets hit in the genitals, they start feeling nauseous and everything?
I don't know. Doesn't it make sense, though? I think it's just because it hurts a lot. You know?
And our body associates pain with a gag reflex.
I don't know. Some people do. I don't know. I don't think I've ever vomited from pain. But I know what you're saying. And I think it's just because it hurts a lot. Pretty sensitive. Okay, let's talk for a minute about this cerebellum and these sensory inputs that it gets. I think I've talked about this a little bit already. But the cerebellum is what really makes us so that we can move smoothly and coordinatedly. Okay? And so the cerebellum gets all of this proprioceptive information. And here's the way that information comes. It comes up here through these sensory nerves, comes up through these posterior spino from the spine to the cerebellum, spinocerebellar tracts that go up this way into the pons. And in the pons, it takes a right-hand turn and goes out into the cerebellum here. The cerebellum processes all that information, and then it sends the information either on up to the brain or back on down to the muscle groups to keep everything working. Now, most somatic information is relayed to the thalamus. I think that's an important point for you to remember. But only a small fraction of the information that is sent to the thalamus is then passed on up to the brain. Okay? So the thalamus forms a very important screening system so that we don't get overwhelmed with too much information. TMI, too much information.
So someone who has like autism or some other sensory overload disorder or whatnot, they have something wrong with their thalamus, or they just have an overactive thalamus, or?
I would not be able to tell you the answer to that. I don't know what autism is caused by. I don't know what the deficit is, and I'm not sure anybody does. I think it's still a huge research issue. I know one thing it's not caused by.
Vaccines.
Vaccines, that's right. Just a quick mention of interoceptors. Remember, interoceptors are the ones that come from inside of us, from our inner organs. They are not very numerous, but they do involve nociceptors, thermoreceptors, and baroreceptors and chemoreceptors. But just so you know, there's not very many of them, and you don't experience this very often. It almost never gets up to our thalamus. How does this stuff get from inside of our belly up to our brain? Well, it usually jumps on one of these nerves, and a lot of them are cranial nerves, This is the big one it jumps on. It jumps on the vagus, the vagabond, remember? So although the vagus nerve carries information down, it also carries information up. I've got 2 minutes, but I'm going to take 4 probably. Somatic motor system is the control of our somatic muscles, which is our voluntary skeletal muscles. The autonomic nervous system, or the ANS, is the one we will talk about next chapter. It's the automatic system, and it controls things like smooth muscle, cardiac muscle, and glands. I apologize. Excuse me. So let's talk about the motor system carrying information down real quick, and you can probably relate this to patients that maybe you've seen in your life, or friends and family that you've seen in your life. Has everybody here seen a patient that has cerebral palsy? Okay, and cerebral palsy patients have perfectly normal brains, okay? Their brain works just fine. They just can't send the signals out to their muscles. So they kind of sit there like this, and then talk really funny, and their face is all contorted and so forth. The problem with cerebral palsy is with their upper motor neurons. Now, most people have 2 motor neurons. You have an upper and a lower. So whereas the sensory system takes 3 nerves to get the message up, the motor system generally just takes 2. And the 2 are the upper motor neuron, which carries the information from your cerebrum down. Now, why do cerebral palsy patients have problems with that first one?
Balance.
Most cerebral palsy patients are caused by anoxia at birth. Okay? They had a lack of oxygen to their cerebrum for a few minutes during delivery or whatever that gave them that problem. Okay? It's nice to see that that number is going down, but just so you know, I read a thing last night in a newspaper that the incidence of brain damage and cerebral palsy is 10 times higher in birthing centers than it is in hospitals. 10 times higher.
It's huge.
So,
Huh?
So that's huge.
That is huge. Kind of makes you not want to have a baby in a birthing center. I was a doctor out in the Dalles, and there was a lady who wanted to open a birthing center out in the Dalles. This is 20 years ago, and the doctors on the hospital staff voted it down. We didn't want to be associated with it. And the reason was that in the previous 2 months, 2 babies had been born at home with midwives and brought in dead. What happened? They didn't have suction. They couldn't suck out their little mouths to get the snot and all the stuff out of their mouth, and the babies suffocated and died before they could get to the hospital. So being at a hospital may not be the place you think you want to be to have your baby, but let me tell you, there's a lot of reasons that it's really nice to be there. And the 2 main ones, in my opinion, are that you have suction and you have oxygen. Okay? And during those first few critical moments of life, nothing could be more important. But anyway, I'm not trying to go on a rant against nurse midwives because I think most of them do really well. I just would never want anybody to have their first baby. I think primates probably should always be born in a hospital today. After your first baby and it goes well, that's okay. I think midwives do a good job. All right, anyway, let's go to this upper motor neuron. We were just talking about it in terms of cerebral palsy. And then it goes to the lower motor neuron, which is usually found in the brainstem or the spinal cord, and it sends the message down to the muscle to actually contract. It usually crosses over and then and at the pyramids, which is in the medulla oblongata, and goes on down. There are 3 tracts that carry this information. You do not have to know those. Just know that it's a motor tract. So is it in the top half or the lower half? It's in the lower. That's right, because the lower part, which is the ventral area, is the motor. The motor homunculus is different from the sensory homunculus, and it looks like this. And you know, this is all pretty small back here. You don't have that many muscles in your butt, and your legs just have a few muscles comparatively. You get out here and your thumb and your fingers are pretty sensitive. They have lots of little muscles that are very important to be able to control very well. But then the two biggies are your face and your tongue. You have to be able to move that meat around, remember to chew it, and your tongue is very talented from a motor point of view, as well as your lips and so forth. But the biggest thing of all is actually your larynx. Now think about how complex your larynx is. Think about me saying A, B, C, D, E, F, G. And think about how many thousands of muscle fibers have to be fired off and relaxed in order to change the tension of my vocal cords in order to be able to say those words. There is an incredible amount of motor input that goes to your larynx to enable us to talk. That's why the larynx is so big. So these paths come down this way. Here's these cortico-bulbar tracts come down here. They all cross over as well down here lower in the pyramids of the medulla. And then they go on down here and they go out through the ventral roots out to the body. Now, if the lower motor, here's the key point. If the upper motor neurons are damaged, you may either get too much contractions, like the cerebral palsy patient, or not enough, like the patient with ALS. Okay? Who's that scientist guy?
Stephen Hawking.
Stephen Hawking. He's got ALS. Lou Gehrig had ALS. They can't move it at all. Okay? If you have damage to the lower neurons down here, you're flaccidly paralyzed. If you don't have the lower motor neuron, it's only going to go one way. It's going to be no function at all. If you have damage to the upper motor neuron, it can be either. It can be either too much activity or not enough. Okay? Once again, take a look at these routes that you take, but I think we've discussed that. Imagine the control necessary of your arytenoids, remember those little cartilages, to create every letter in the alphabet and every zone. I think cerebellum, let me just show you one thing. It's called the Romberg test. One of the tests we do in medicine a lot is called the Romberg test. You just have a patient close their eyes and stand there. And I think I'm fortunate enough to say that I still have an intact cerebellum so that I can still balance pretty well. But with my eyes closed, you see, I'm probably moving around just a little bit. There's a little bit of sway in here, right? But if I open my eyes, sway goes away. Now, why is that? Because I have more information going into my cerebellum when I have my eyes open than I do when my eyes are closed. So when my eyes are closed, I'm relying on all these other senses, which is proprioception and so forth. And I probably will be swaying a little bit. Another test that your friendly state trooper will do on you if you get pulled over for suspicion of DUI. Last thing, real quickie, don't take notes on this. This is simply a little business about the spinal cord and neural tube defects. You know, I told you from the beginning that you need your neural tube to close over. It occurs in a bunch of different levels. If it just closes like this, but everything is okay underneath, here's the spinal cord, here's the dura, here's the nerve roots. This is spina bifida, because the spinal cord the bones did not form all the way around. The next one is where the dura extends out of but it doesn't come through the skin out here. Here's a meningomyelocele, where everything comes bulging out. And then finally, the last one, where it doesn't close at all, there is no skin over it. And then I've got some pictures. This is the worst stage of all. This is called anencephaly. I think I told you the story of me going on the kidney transplant flights to get the kidneys out of a baby that's born like this. It's a sad, very sad thing. These children have no brain. They generally live, they're living on their brain stem. They usually live 2 days at the most. It's a really tough deal. If you want to look up something really sad, look up anencephaly on Google. And there's a lot of parental support things. This is the next stage of that, where it closed over up here, but it did not close over down here. So these babies' spinal cords are out here on their back, and they're usually, well, they're always paralyzed from here down. Big problem. If they're worse, the biggest problem is if this erodes through and leaks cerebrospinal fluid, then it's a chronic meningitis problem, and these babies don't live very long either. They're doing surgery in utero now. When they diagnose this thing with ultrasound, they actually can do surgery in the uterus and try to free up the skin out here and the skin out here and kind of close it over so they have something covering them, which is a wonderful thing, because then sometimes they even get some neural function and they're not totally paralyzed down here in the lower part of their body. This is a patient with hydrocephalus. Hydrocephalus means too much water on the brain. That either means they're making too much CSF or they're not reabsorbing it enough, right? That's treated with a shunt these days. You take and put a little plastic tube here into the ventricle and run it out through the skull and then underneath the skin and then underneath the skin and then underneath the skin down to about here and then drop the end of the tube into the abdomen. And so the extra fluid, just working on pressure, flows out, comes down here, and these big ventricles shrink down to normal size and can work pretty well. This is a stroke. This is a piece of dead brain out here from a blockage of a blood vessel. This is what the most common cause of stroke is. It's caused from arteriosclerosis in the carotid arteries and little clots that form here and get flicked off as an embolus and go up and block off the blood supply to a certain part of the brain. Here's another example of a stroke. This is a bloody stroke. You can see it's really dead. This is a big cerebral aneurysm. This is the circle of Willis that they've taken out in an autopsy specimen. And here's a big aneurysm right here. When these aneurysms blow, it's like taking a fire hose and shooting it into your brain, because it's coming out of there at 120, 140 millimeters of mercury, and it's just going right into the jello. So it just does a tremendous amount of damage. Here's a cerebral aneurysm picture on angio. Here's the post-mortem specimen of that case. This is Alzheimer's disease. The biggest problem in America today is Alzheimer's because more and more of us are living longer. There's a set of webbing that occurs so that the normal connections between the brain cells don't connect normally. We're learning more and more about it. Hopefully, there's a number of medicines that are being tried. We put my dad on it. He couldn't stand it. He said it just made him feel too weird. This is a patient with multiple sclerosis. It shows up as areas of plaque formation on the brain. Okay? All right, so we will do the autonomic nervous system tomorrow, which is